Hello, everyone. I am very excited to introduce our Health Privacy Challenge, which was actually launched for the first time this year within CAMDA. So I would like to thank David and Pavel for giving us this space to discuss the challenge and its outcomes. And I really would like to acknowledge the ELSA project. So it's a very large European collaborative work on building towards safe and secure AI models, and it incorporates multiple institutions. And as a part of EMBL, we are very interested in health data, so that's why our efforts were towards benchmarking privacy-preserving generative models for gene expression data sets. So as Antti already set the stage for me very nicely, but I will still like to emphasize that even though we use the synthetic data as a way of having a private data set, that it doesn't actually mean that synthetic data sets are always safe. So one of the reasons is overfitting is an actual issue. So many of these generative models have a tendency to overfit, and this means that your model can basically memorize some of the data points, and this already means a privacy leakage for that data point in your data set. And of course, the adversaries are getting more stronger each day. There are new threats coming up. So it's very possible that these new adversaries can exploit these subtle signals and patterns in your trained model for re-identification of the data points. And finally, just assuming that we have a synthetic data, this might give us a false sense of security, but on the other hand, if we do not really run rigorous tests, that we might actually see that our synthetic data is not private at all. And especially in this challenge, we were focusing on the gene expression data. And why is that? Because first of all, it contains very rich biological signals. So this means that there might be actually a signal about a donor as gender or ethnicity or any type of phenotype that can be identified within this data set. And among the many privacy-focused studies, there is a benchmarking towards different data types, including images, text, also some from the medical domain, but RNA-seq is, even though it is relatively, at least for the bulk RNA-seq, a more straightforward data type, it's actually underexplored. And connecting to that point, because, for instance, bulk RNA-seq is relatively, compared to more heterogeneous, like medical records type of data, is much easier to adopt. It's actually a nice way of initiating people from other communities, like privacy community, who have never worked with health data before. So it's actually a very nice use case for them to get started with the domain. And finally, for the gene expression data set, in the challenge, we used both bulk and single-cell RNA-seq, and it actually created a very nice gradient for us, a complexity gradient, because in the bulk data, we have an average representation per donor, but when we move to single-cell data set, then we have basically thousands of cells for each donor. So we kind of try to also explore what this means when a donor has thousands of cells in terms of privacy. So maybe just going over the contributions of the challenge, we first set up a GitHub page with baseline models, both for generative models and also for membership inference attack models that are already available in the literature. And then we also provided very wide range of evaluation metrics I will mention. And basically, we asked the participants to start with this starter kit to help them simply first run the baseline methods, and then when they develop their models, they can use the evaluation metrics immediately. If you're also interested in generating synthetic data, please take a look at our GitHub page as well. So it should be reproducible, or let us know if it is not. So this is how the participants started with. And then we have the ELSA's own benchmark platform. So this is actually where we provide or redistributed the gene expression data sets. They are publicly available after signing a data download agreement. And it's actually a living benchmark platform. So it is, even though the challenge has ended, it is still there. And again, if you are interested in testing how in terms of utility and privacy, how good your synthetic data, you're welcome to submit your synthetic data sets, and you will see evaluation involving multiple metrics. So very briefly introducing the task tracks in the challenge, which I will go into a little bit more detail later. The whole aim was basically to benchmark synthetic and private data generators for gene expression, and the first track solely focused on bulk RNA-seq data, and then we run it in a blue team versus red team setting. So the blue teams were tasked to generate the synthetic data, and the red teams were tasked to launch attacks, the membership inference attacks to the synthetic data. And the second track was focused on the single-cell RNA-seq. And again, this is a more complex data set than the bulk. We kind of encourage the participants to have more free form to explore what is privacy in this setting, how you can generate a private synthetic single-cell data. A little bit overview of the participation. So as you can see, there was more attention to the bulk RNA part, which constitute the track one than the single cell one. And my guess is, again, also mentioned in the beginning, the bulk RNA-seq is kind of a relatively easier data set to start with in this type of experimentation than single cell, especially, again, people from non-bio communities. So this is what I'm attributing to the interest more in the track one. And when we compare within the track one, we see that, again, now there is more interest in the blue team than the red team. And again, this might also come from a lot of us might be working with generative models or in some way train a model, but building and trying to work on an attack algorithm is something that might be a little foreign or something that might sound more complicated. So again, I attribute the difference to a little foreignty and then complexity of the red team task. As mentioned, the track one ran in a blue team versus red team setting, and it had two phases. First, we actually needed to collect the blue team submission. So we provided the participants with a gene expression data set, and just like in a regular machine learning pipeline, they separated the data set into training and test. So in this case, training means a member and non-member, going for the red team jargon, because this means that the training data set is what the generator model sees. And then using this trained data, they generate a synthetic data set, and this is the end of phase one. So this actually took around 2 months. So there was a 2-month window to submit this blue team methods. And afterwards, we collected, so we shared first the generative model, completely white box. The only thing that was unknown to the red teams was basically which of the data points were used in the training data set, so member data points. And then we also shared the synthetic data set. And of course, since the whole gene expression data set was already public, and that was their test data, basically. And for the red team task, it also ran almost around 2 months. And the idea was, simply predicting whether a given sample in the test set was used to train this generative model or not. And finally, we also had this deadline from CAMDA to submit extended abstracts, which I found quite useful because as you will see when I will just introduce a little bit more about evaluation metrics, it's very difficult to judge how a model does just looking at a leaderboard, because one model does good in several metrics and then the other model does better in other metrics. So having an abstract submission and also investigating the ideas and how they think through their methodology give us a really nice grounding point to understand them. So we used two bulk in the track one to use two bulk gene expression data sets. They were all from TCGA, so we simply redistributed them. And the first one was a breast cancer data set, and the second was a combined data set of 10 different cancer tissues. And here, there are also challenges within these two data sets too. So in the first data set, because it is a rather smaller data set and focuses on single cancer type, it might be a little bit more challenging to train, first of all, a model on a smaller data set, but also trying to predict a subtypes of a certain cancer compared to a larger cohort, even though it might be easier to train the model. And then it might be also even easier because we have separate types of cancer. So there are different types of complexities while even working with the bulk RNA-seq2. So this gave us also a nice look at evaluation metrics across different methods as well. And for the evaluation metrics, we try to target multiple dimensions of how valid the synthetic data set is. So we mainly try to capture utility, fidelity, biological plausibility, and privacy aspect. I won't go into much detail about all of them, but for instance, just giving a few examples, for the utility, we basically measure how well this synthetic data set does in a downstream task when you would use your real data set. So for instance, for breast cancer, this is predicting breast cancer subtype, and for the larger cohort, it would be predicting the tissue of origin. So we would hope that the synthetic data set provide as good as performance as the real data set itself. But yeah, on the other hand, there is this biological plausibility aspect, which actually doesn't exist in other benchmarking studies that are not actually working with biological data, because we also want to keep the biological signal. So recovering the co-expression profile or differential gene expression profile is also quite important for us. And of course, there is this privacy metric. And yeah, as Antti also mentioned, there are many different metrics to go towards how to measure privacy. For instance, distance to the nearest neighbor is a similarity score based, but it's actually not as reliable as membership inference attack in terms of warning us that how at risk we are. So we actually provided also the blue team participants with baseline attack models to see before the actual red teams attack their model, to see before and how private their models are. I will slowly now walk you through this very colorful plot. So this is a plot to basically showcase a little bit of the trade-off between utility and privacy. So we have here in the colorful nodes, I'm not sure if they're colorful enough from a distance, but these are submissions that we got from our blue teams. And the ones that are looking almost red or almost black, maybe, these are our baseline methods. So what we used was basically conditional GANs and conditional VAEs as baselines, and we also included differential privacy on them. And we also used a very simple multivariate normal distribution without any type of privacy. So what you can see is on the x-axis, we are measuring how well a method does in a downstream task. So this is your usual success performance, APR. And then on the y-axis, we are measuring the privacy using the true positive rate, where the false positive rate is fixed at 0.1. So what this means is we actually really want the models not really incorrectly identify data point falsely as a member. So because that might have really bad consequences for the person. So we really set the threshold to really low to see the risk better. And what we want is basically a good model to be clustered around the bottom right side, because this means that they're very good at utility, and they're also very good at the privacy. But actually, we would even want the privacy, the values in the y-axis much lower. So moving on to a little bit on track 2, which uses the single cell RNA-seq. It also ran parallel to the track 1, and it ran slightly a little bit more longer. And again, as I mentioned, this mostly encouraged the participants to explore the data set rather than providing them a very like leaderboard ranking style kind of competition, because as mentioned, this is a very high dimensional data set, and defining the privacy, whether this is at the cell level or donor level, is something that we also wanted participants to encourage. So we didn't really have a leaderboard ranking for this. So again, here the CAMDA extended abstracts were quite useful for us. And for the single cell track, we used 1K data sets. The authors kindly shared and allowed us to redistribute this data set. This is also online in the ELSA benchmarking site, and it's actually online as a separated train and test evaluation form. So if you would like to have a try, again, please go ahead. And this is actually one of our baseline synthetic generator with Poisson distribution. You can see that it's not doing a great job and it's not even private, but this was something we provided the participants to just have a look at the space and the data set itself. And again, for the evaluation metric, we tried to target the same dimensions, but now the metrics change because the whole data set itself is something new. We have to consider different type of constraints when working in the cell level. So we updated our metrics towards that. And for the privacy aspect, because the data set itself was huge, and some of these membership inference attack models are really not designed to scale towards like a very large data set. So we weren't really able to run everything on the whole level. So we ran small privacy tests on a downsampled version. I won't actually give you more information about this, but just to create some kind of curiosity, our participants will be presenting what they did on the single cell part in the afternoon after lunch. So would be great to see you there. So as a future outlook for this competition, yeah, as mentioned, the working with the single cell data set and expanding, so understanding the biological plausibility, because just generating a synthetic single cell data set without considering privacy is already challenging enough. And when we put the privacy on top, then it becomes even more complex. So we kind of want to explore this area a little bit more. And of course, moving toward and trying to benchmark the longitudinal and multimodal data would help us to see what how this works in a more real life setting when we work that type of data. And again, I think as Antti already mentioned, that moving a little bit more beyond the generic risk measures, but to really consider what are the needs of the biological domain or the clinical domain in terms of this both evaluation and maybe building even different type of attack models would be something we're very interested in. And I think, again, this session really provides us one of the really good steps as trying to strengthen the connection between the bioinformatics communities and also privacy in AI communities. And we really hope to work towards this. And I would like to acknowledge our amazing ELSA team who actually worked towards designing and creating this challenge. And we were very happy to have a lot of support from multiple institutes. So I'm very grateful for them. And yeah, we will have a panel discussion next about, again, focusing on health privacy with very fantastic panelists. And then we will hear from our participants in the afternoon. So I'm hoping to see you there. Thank you.
Questions?
Are you considering running common things or say genotype data, somebody genotype data?
So first of all of the data we actually share with the participants are already in a way public. So we really put great care to not really encourage our participants to work on a data that is actually private and then simply share it. But if we were to move towards that, we are thinking of updating our benchmarking system so that participants would just build their models, but do not have a direct access to the data, so it might run in a, for instance, in the background in a Docker environment, so that type of thing. But directly sharing this type of data publicly won't be possible. So we might work towards changing our benchmarking system if there is an interest towards working with that.
But there are public genotype data resources like Thousand Units, for example, is very well known.
Yeah, thank you.
Hi, thank you for the nice talk. I'm sure like the submission to God can like give you a composite answer, but that you kind of the connection between like model complexity and privacy, so see more parameters.
So actually, we didn't quite benchmark this, but we were really considering whether at least, again, this is also part of participants having an abstract submission. So we kind of also encourage them to mention the model complexity and maybe runtime requirements. But definitely, if we would like to see whether there is some type of correlation between how large the model is and how overfit that's, and how whether it is reflected in privacy or not. But yeah, definitely. Thank you.
I guess, I mean, with differential privacy, there doesn't have to be a correlation. And some of the solutions obviously use that. So.
Yeah.
Any other questions? If not, maybe we'll start with Hannah.
Yeah. Then.